Welcome to the pre-lecture video for lecture 4. During this pre-lecture video we're going to have a recap on sampling and the idea of statistical inference, and then I'm also going to introduce the idea of something called the central limit theorem. So statistical inference. So whenever we do any study, we're going to create some sort of estimate of our sample. So far we've mainly focused on things like relative risks, odds ratios, maybe a proportion or percentage, a mean, a median, but there are lots of other estimates that we've not really focused on and probably won't during this course. When we get that sample estimate, let's say we get a mean from the sample of individuals that we collect data on. Do we think that that mean that we generate from our sample is going to be exactly the same in the overall population that we sampled from? Remember, we don't have the opportunity to ask every single person. We take a sample from the population, but really we want to talk about the population that we drew the sample from, not just the individuals that we have data on. So do we think it's going to be exactly the same? And our answer really is going to be no, not exactly. But if we don't have a biased sample, our sample estimate, our estimate that we generate from the data we collect, should not be too far from the population estimate. So thinking about this slide again that we saw in the very first lecture, we have our population on the left. This is who we actually want to talk about. We might want to talk about everybody in the UK, but we can't collect information on everybody in the UK. So we take a subset, a random representative sample, and we actually collect information on all of these people. Then what we do, we analyse that sample, and that's where we're at the moment. If we could just believe that our sample is exactly the same as a population, we could stop our statistics learning now. We could say, right, that's it. But in truth, we know if we want to talk about this population over here on the left, our sample is not going to be exactly the same. We're going to miss the true estimate, let's say the true mean, by some amount, just by chance, just because we've got a certain number of people in our sample that might be ever so slightly different. So we take a representative sample. As much as we desire it, it's not going to be exactly the same as what the population will be. Therefore, the estimates that we could get in our sample will miss the true population estimate just by chance. So we need something extra now to account for that uncertainty. Because we still want to talk about the whole population, we're saying our sample estimate is not exactly the same as the population estimate. There's going to be some uncertainty, and we need to try and account for that uncertainty. The central limit theorem is one of the main theorems in statistics, and it's the main thing we consider when we're talking about making this leap from sample to population. It is a theory, so it is a bit brain-tingly. We have to think conceptually. There's a lot of algebraic equations in the background that explain this, but that's not going to be very helpful for us. We want to get a general idea of what the central limit theorem actually means. So let's just imagine for an instance. We are interested in measuring the heights of all first-year medical students in the UK who started their medical degree in October 2019. So that's what we want to talk about. We want to say, what is the average height in all medical students, first-year medical students that started in October 2019? And we're in a very rare position, a position that we're not likely to be at in everyday studies. Let's just say we measured everybody's height as they started medical school, in every medical school in the UK. And let's just say, for simplicity, there were 7,500 individuals that is talking about. So we've got those 7,500 individual height values. We analyze that data, we analyze those heights, and we find then the mean is 175 centimeters. Note here that I've also put population mean, because the population we want to talk about, we have all of the data. So this is no longer just, well, it's a sample mean, but it's also our population mean. We want to talk about how spread out those values are as well. So we're going to talk about a standard deviation, and we get just under 8 centimeters. Again, we've got all the information on everybody, so it's a population standard deviation. And to get a bit more of an idea, the smallest, or rather the shortest person in our population was 145.7 centimeters, and the tallest was just under 210 centimeters. Of course, this is a theory. We have to imagine that this is the scenario. We're not really going to have all the values of everybody, but this is just to explain where this theorem comes from. Obviously, I want to display this data. It's much easier to digest what's going on here. So this is just repeating the values from before, but now displaying it as a histogram. So here is my 175, my mean. Look what's happening here with this data. Once I plot the frequency, it's not perfectly normal, because this bar would be over here if it was, but it's approximately normally distributed. I have my mean here in the middle, at the peak, the top of the frequency, and I do have some shorter and some taller people, but they're in roughly equal proportion and a smaller frequency on either side of this distribution. Got my standard deviation here as well, just telling me how spread out these values are. You may have noticed that I'm not using X bar here for the mean. Remember that X bar means sample mean. Here I'm talking about a population. So when we talk about population values in statistics, we use the Greek alphabet. So this is the Greek letter M, or mu, for mean. This here is sigma, or the Greek letter S, for population standard deviation. So these are all our heights of our 7,500 students. Okay. But in reality, I'm only going to take a subset from the population. I'm not going to measure 7,500 individuals on their height. What I'm going to do is I'm going to take a smaller subset. Maybe I'm going to pick a couple of medical students from different medical schools, or I might pick one medical school and take a few students from there. But let's just say I might just collect information on 20 students and measure their height. When I take those 20 students, I could work out what their sample mean is and their sample standard deviation. So in this sample of 20 students, I find that their mean height is 176.5. That's not exactly the same as what the population mean is, but I wouldn't expect it to be because I've taken a subset from that population. It's likely to miss it a little bit. But really, unless I have a biased sample, unless these 20 individuals that I collect are biased in some way, I wouldn't expect my sample mean to be too far from the population mean. Now, let's just say I've done my one study, let's just say if I was going to do another study, I'm going to take a second sample of 20 individuals and work out now what their mean and their standard deviation would be in that second sample. Of course, this seems a bit odd. I wouldn't really do this in practice. In practice, I do one study, and that's the information I have. But this theory is going along the basis of, okay, well, I've done one study, I get a mean and a standard deviation. Now if I do a second study, I'm going to get a different mean and a different standard deviation. And that mean probably won't be the same as the first study. The mean in the second sample also probably won't be the same as the population mean. And here it is, a different set of 20 students, and now their mean height is 178. It's a bit higher. The students that I've sampled from in this second study have a slightly, on average, higher height, taller height. And I continue. Each time I do a different study, 20 people, I get a different mean, a different standard deviation, and I keep going and going and going. And to infinity. This is the idea, this is why it's a theory, it's hypothetical. So let's just recap. If I did multiple repeated studies, each study will have its own mean. Now, let's just try and think a second. If I'm going to take all of these means from all these different studies, and I plot all those different means in a separate graph by themselves, we start to see something quite interesting. So this here, I've removed the bars from that original graph. This here is a distribution of those 7,500 individuals from the whole population that, remember, I wouldn't have in practice. What we're saying with this theory is if I was to take repeated studies, and in each of those studies I get a mean, then if I'm going to plot those means, let's say I might get one study down here, in a second study down there. I had one where there was quite a high average, a high mean height. The fourth study might be down here, fifth one, sixth one, seventh one, and so on. I'm quite unlikely to get a mean down here or up here. And the reason for that is then that the 20 students I get would have to have an average once they've been balanced out with a mean that would put them down here or up here. So I'm going to have to be quite unlucky to sample 20 students from this sort of region that when I work out their mean, on average, it's about 155, say, and the same follows up here. So most of the time, I'm going to get a mean in this central region. Okay. What's starting to happen is that these means that I get from my studies, once I start to balance it out, they're starting to be around this middle section, around this central bit here, which, if you can remember what the mean was in our population, it was 175. So what's happening is, if I take repeated studies and each time take their mean, if I was to plot all those different means, they're going to be based around the true population mean. They're going to be normally distributed again. Look, because I have most of my frequency in the center of this little mini distribution and only a few on the extremes. It's going to look something a bit like this, where the higher frequency in the middle is exactly the same as the true population mean, 175. So when I plot the sample means, they will be close to the true population mean. They'll hover around what that true population mean is. They'll be less spread out as the observed values. There wasn't as much variability, because to have more variability I'd have to sample individuals that when they average out would have to be quite far in the extremes, which is quite unlikely because a lot of the frequency of the observations is around the true population mean anyway. They're also normally distributed around the true population mean, and sometimes the sample means will be an over or an underestimate estimate of the true population mean. But they're going to average out around the true population mean. And it's unlikely that in any of the little samples that I take, once I work out those sample means, it's unlikely that any will be exactly the same as the true population mean. They're all going to miss it to some degree. Just like when I do in reality my one single study, I'm not expecting that it will be exactly the same as the population mean. But I don't expect it to be too far away unless my sample is biased. So what does all this mean? Well, whenever we do any study, my sample mean is my best guess of the population mean. Just to be clear here, we're only talking about means in this scenario, but it follows for all the other estimates as well. For odds ratios, relative risk, proportion, all those different estimates, this same idea follows. So when I do my one study, the estimate here, the sample mean, is my best guess at what the population mean is. But if I was to repeatedly resample, each time taking the sample mean from all those different samples and plot those means, they would be symmetrically or normally distributed around the true population mean. I can use this idea to think about how precise my one sample mean from my one study that I'll do is. To get an idea roughly how much have I missed the true population mean with my one sample mean. And we call this idea of precision standard error. Standard error. It's very different to standard deviation. They mean different things. Standard deviation is descriptive. It describes how spread out my values are. Standard error relates to the precision of my estimate, and it's the main thing I use, the main calculation I work out to make the leap from sample to population. What we're going to do in the lecture is I'm going to show you how we calculate the standard error, but more importantly how we use that to create confidence intervals and subsequently p-values to infer about our population, and try and think, okay, we have our one sample, what is likely to be going on at a population level? How precise is my sample estimate? This is the end of the video for lecture 4.